Innocent drop.
Yeah.
I'm blank. You could pause the lines. Yeah, you have your goals. That's what it's so much fun. But yeah, after about 2 months ago, we had like that every month. But then doing. You know, people actually go to find any side of the figures to find that are running. That's the reason why you see how much that's going to change. Stock fund have to do this. It's extending. Everything's really. They got to wait. But it's got to go across in there. Then they got to wait. Why they just say money. And that's a thing.
Good morning. We have a lot to get through today, so I want to just get started. So first things first, some of you are working towards your exam 2 take home submission today, right? I saw 8 submissions this morning. Please get it in by midnight today, okay, 11:59, okay? That will of course help you get at least 40% of the points and whatever you get on the class version. So hopefully you'll get a decent score in the end. It's not compulsory, it's optional. I hope everybody is aware of that. Any questions about the take home submission? The exam 2 take home submission. Any questions? Okay. Next announcement. Your project is due by Thursday at midnight again. Are we all making progress towards the project? Each group, you should recall that I told you no extensions. So if it's not in by midnight on April 16, that is by 11:59 p.m., your group will get a 0. So I hope I don't get any request for extension or excuses or anything. Is everybody okay? Are we all on track towards that? Just give me your kind of nod so that I know you are confident you'll be able to make the deadline.
We had catastrophic failure last night.
Catastrophic failure.
Catastrophic failure.
What were you trying to launch a space shuttle?
It was like 1 second behind me.
Okay, I hope you can still make the deadline. Can you?
Yeah, yeah.
If good, I just spoke with him about that.
Yeah.
And I gave what you may call as a pivot. Okay. I gave you the option to become an unsteady. Okay. All right, good. So that's good. Then so far in the class, I have done 7 participation scores, one of which was an attendance for coming to the project discussion. So that's 7 points that most of you should have gotten. Okay. And then I'm going to set aside 3 points just for doing the course evaluations. That is, you do the course evaluation, take a screenshot of the confirmation page that your evaluations have been submitted, upload that, you get 3 points. You can tell whatever you want in the evaluations, of course. It's just for you to tell me that you have done the evaluation and show me the confirmation page, you get 3 points. Okay, that's one way to collect data from this class. Regarding exam 3, okay, exam 3 is going to be scheduled on the last day of class. I want to show some resources that I've posted related to exam 3. So if you're listening, please go to files. I sent this by emails over the weekend. So what you can find here is, let's see here, this exam 3. Yeah, so this is exam 3 mock. Okay, it gives you exactly what you need to do. How you should think about it is, if you find 5 problems here, do very similar problems from the suggested set. Okay, that's how you prepare for it. I also have posted the solutions for the mock exam. So it's given to you so that you can actually go over the problems first, then look at the solution, and then make sure you are able to do this under reasonably similar conditions to the test, so that you time yourself, you see that if you are able to do this. Okay. And at the last lecture, that is April 28th is our exam. 23rd, April 23rd, Thursday, I will go over the mock exam in class. I'll spend about 45 minutes going over it because I've already provided the solution, but I'll still try to take you through the last steps and get you to the answers. Okay. Any questions about exam 3 preparation? we still have to discuss module 7, which is my next item of discussion. Okay. So for module 7, I found that in fall 2020, I had recorded lectures for the entire course. Where is that? One second. What's happening? Okay, but so please listen. In fall 2020, I recorded lectures for the entire course. So if you click on this link on the syllabus here, you'll go to YouTube. Where is that? Okay. Okay. So here is the YouTube page where I have this from fall 2020. In fact, I have lectures all the way from module 1 to the end. So if you scroll down and find module 7, these are not very long videos, 10 to 20 minutes. Totally, the runtime might be like 1.5 hours tops. So I ask you to watch this. Okay. I'm going to go over important elements of module 7 in class, but we have only 3.5 lectures to do this. I would want you to watch this, learn the material from the lecture, and we'll discuss it and do problems in class. Make sense? Okay. And to make you watch this, I've introduced another kind of viewing exercise, which is worth 5 points. What you need to do for that is view the lectures and make a good faith statement that you have viewed them. I'm not going to collect any proof, but all I'm asking you to do is view the lectures on module 7, and by Monday, basically make a small written statement on Canvas that you have viewed it, and you get 5 points for that. Now, you may do this without viewing it. You'll still get the 5 points, but the hope is you will view it so that you can actually learn the material. Okay, 5 points just for viewing the lectures on module 7. This is due by Monday, after your project is out of the way. Is it clear? Questions? Okay. So we have covered exam 3, or we are talking about module 7, which we'll go through in the next part of the lecture today. Exam 3 is going to be in class, similar to the previous 2 exams. The remaining thing is that comprehensive final. Now, I got maybe 4 or 5 people tell me they would prefer a take-home final, and then there were some who said they need more details about what that final will entail and so on. So I did prepare the final, okay, and I did something which may be surprising. So what I did was to actually post that final already on Canvas. So let me pull it up here. So this is your final. It's already on there. You can start working on it today if you want, or if you can. It's due by May 4th at midnight. Okay. It has only 2 problems. One problem is related to control volume analysis, and one problem is related to the related to pipe flow, where you have to calculate flow losses. Okay. So this is on there right away. All right. Okay. Actually, I also posted the solution, so I should go on there and delete it right now because the solution is also there. I need to create a different file. But the idea is this final is already posted. It's a sort of a lengthy problem which requires you to think a little bit, but you get 3 days to think nominally. But I've posted it right now, so you can start working on it as you learn the material. Okay, so module 3 will test you on exam 3 will still test you on module 7. And final exam basically takes a broader view of the course, tests you on 2 topics. One is control volume analysis, other is pipe flow, which I think if you have finished this course, you should be able to do those 2 problems, given the time and the space to think about. Okay, so in terms of weightage, I've made a slight adjustment. So what I have done is to make the final worth 20%, same as the project, and move 5% from the final for viewing the lectures on module 7. So that everything adds up to 100%. Okay, so the easy scoring opportunities that you get are, you get 3 points just for doing the course evaluation. You get 5 points for viewing the lectures on module 7 and making good faith attempt to follow the material. And for the take home final, we are going to have 20%. For the project, we are going to have 20%. Questions? You had some questions about the final,
You answered them pretty.
so you're okay? Yes.
So when we go to turn in the final, how do you want our submission? Like, do you want to?
Handwritten solution
Okay,
can upload it as a PDF.
Okay.
In fact, the system will access set up only to accept PDF file.
okay.
Okay. So what is sort of a non-trivial or a little bit of additional layer of work is watching these videos. That is, there are actually like 15 parts, but each part is on an average 10 to 20 minutes, maybe even shorter. So you are essentially going to spend maybe 2 to 3 hours going through the videos and have your, just like class, have a notebook, write down the material. It gives you the additional convenience of pausing and rewatching and so on. But make the attempt, set aside 3 hours, watch the videos, go through the content, and when you come to class, it will help you follow the examples that we do. Okay, I am giving you time until next Monday to watch the videos, but don't push it until Monday. Start doing it, at least spend 20-30 minutes each day. So that 6 days, you basically do the work. Spend half an hour a day watching these videos. Is it okay? Not too bad. Okay. Other questions before I start with module 7? Did you have a question? Okay. So as far as submissions go, what's coming up today, your exam 2 take home is due. Thursday, the project is due. The final is due on May 4th, which is Monday. Okay, May 4th is a Monday by midnight, which means we won't have a final at the allocated slot. So no final, no coming to class again after the last day. The next stop is you upload your take home final and you're done with the course. So if I receive all the submissions by May 4th, hopefully by May 5th and 6th, I should be able to complete all the grading and post your letter grade. That's the hope. Okay, by May 6th, I want to be able to complete this. Okay. All right. So let's see here. I have 10 submissions so far. That's pretty good. That's more than half the class. So I hope the remaining 9 people or 8 people will still consider doing that. Okay. All right. Let's go back. So having said that, there are lectures to cover the material for module 7. I want to use this time essentially to touch upon the topics briefly and start doing more numerical problems. Okay. In fact, if you go back to the mock exam that I posted, let me quickly pull that up here. For exam 3, I did post a mock exam. Sorry. Should have done this first. So this is the mock exam for, mock for exam 3, although it's written number 1 here. So this exam contains 5 problems. The first 2 problems are related to scaling analysis, and last 3 problems are related to pipe flow, which is module 7. Okay. So we are going to learn some important concepts. I'm going to touch upon them here, but a more detailed explanations are provided in the recorded lectures, in which I spent much more time. Okay. So I'm sorry, it's not ideal for you to make you to watch more videos, but I think it's necessary given the time constraints we have. Okay. So speaking of pipe flow, can we start with some examples on so what is tube flow and where we encounter it? Or where are instances where you encounter it? Or yeah. Pipe flow, tube flow. Come again? Plumbing. Plumbing around the house where you have a pump to push the fluid around, or if you live in a city where the municipal facility has a huge pump that pressurizes the water and delivers it to your house, you essentially have to you're basically handling water, or what we call running water. What about plumbing relates to fluid mechanics? What are the ideas that we typically learn in fluid mechanics that applies in plumbing?
What I can think of is like a water tower in a city.
Okay,
Water.
city has a water tower. Okay, or the city might have a pumping station, both of which serve nearly the same purpose, which is in one case you increase the pressure by increasing height. In one case you use a pump to increase pressure. Increase pressure or kinetic energy of the water. Okay, so when you talk about water tower, how do you determine at what height to put it? Not just a question for him, anybody can answer. Yeah, go ahead.
Well, the higher it is, the more potential energy the water would have.
So height basically gives you the pressure difference, so that pressure difference will drive the flow. So we all know that flow is driven by a difference in static pressure. If there is a pressure difference, there will be a flow. We know that, right? So can we get more examples of instances where a pressure difference drives a flow or a pump drives the flow? Think around the house, think about your own body. Heart.
Your heart.
Sorry? Yeah, heart. So heart is basically a biological pump that circulates blood in your system. Right? How many of you know a little bit about heart disease and cholesterol and arterial blockages, heart attacks and stuff? Why do people get heart attacks? Yes? I want the engineering answer. I don't want bad habits, alcohol, stress. I don't want any of the medical crap. What's the engineering explanation for a heart attack? Mechanical engineering explanation.
Too much strain on the heart.
Too much strain on the heart. Why there is too much strain on the heart?
Because it doesn't have enough blood to pump.
So think of your heart as in a very abstract term. Think of it as a pump which takes low pressure blood that's coming in. They call it the venous side, and it essentially pumps it, increases the kinetic. A pump is basically a machine to increase kinetic energy. it increases kinetic energy or increases it to high pressure, and then it pushes it on the arterial side. There is, think of it as the heart essentially pressurizes the blood. It gives it kinetic energy so that it can flow through your blood vessels. Okay. So what happens is when in some vessels, especially on the arterial side, if there is a blockage, let's say you have a artery that is healthy, unclogged, there is no blockage, the flow rate of blood or the flow of blood just goes without obstruction. But as plaque or cholesterol starts depositing here, what happens is you start constricting the passage. If you constrict the passage, then the blood or the fluid has to squeeze through a smaller gap, which creates more friction and leads to more pressure drop, which means your heart has to work more to get the blood to circulate. And as this constriction gets more and more, as the artery gets narrower and narrower, the heart has to do a lot of work to get the pump to recirculate or get the blood to recirculate. And if this gets fully clogged or fully blocked, what happens is the blood just cannot get through, which means the heart will start trying to work even harder. At some point, there is a limit to how much harder the heart can work, and that leads to what is called as a coronary infraction or heart attack. Okay, so this is one of the places where what we are going to learn in this class, that the relationship between flow rate Q depends on the pressure drop over the length of the tubing multiplied by inverse to the viscosity times the diameter to the fourth. We are going to learn this derivation, or we are going to learn this expression, and this expression essentially tells what the problem is. If your body needs a constant flow of blood, that is the same flow rate has to be recirculated, the pressure drop, if you rearrange this, the pressure drop scales as flow rate to the diameter to the fourth power. What this means is, if you have an artery, let's say whose diameter is D, and D is of the order of, let's say, 2 millimeters. Okay, if you start having deposits here, and even if the diameter changes by 25%, that is, if this D goes from 2 millimeters to 1.5 millimeters, a 25% change in diameter of this artery could lead to a pressure drop that is, so if I replace this with Q, 3/4D to the fourth, so that's 4/3 to the fourth power, or 1.33 times to the fourth power. Can we get a number on that? What is 1.33 raised to the fourth power?
0.13, 3.13.
3.13. So this is like 3.13 times D to the fourth. So what this means is the pressure drop in the first case to the pressure drop in the second case for the same flow rate. This is 1 over D to the fourth divided by 3/4 D to the fourth, which gets me I'm doing this right, 3/4 D, 4/3 to the fourth, which is nearly 3 times. No. So that gets me 1 over 3, or in other words, the pressure drop in your heart increases by 3 times. That is, for just a 25% change in diameter of the artery, the heart has to work 3 times as hard. This is the consequence of the fluid mechanics, which tells the flow rate or the pressure drop scales as diameter to the fourth power. Now you may ask me, where did I get this relationship and this proportionality? That's the derivation we are going to see. That's the basic analysis we are going to do. Okay, enough with the heart. Other fluid systems.
Carburetor.
Can we think of something that's simpler to discuss? Carburetor has too many complicated parts. Refrigerator, what happens in a refrigerator? You've learned the thermodynamics, maybe some of you have taken fluids too, sorry, thermo too, right? What happens in a refrigerator?
It's like the refrigerant around the.
Okay, tell me what a refrigerator does. It removes heat from a colder region and dumps it in a hotter region. And to do that, it's obviously against the natural progression of heat transfer. Heat flows from the hotter to the colder, not colder to hotter. So how do we accomplish that? How does a heat pump work? Heat pump is just a term that a heat pump is not a single thing. It's a term used to describe many things that work together. So what actually happens?
Does it raise the pressure to increase the temperature or?
I'll rephrase the question for you. If you just find a high school student who asks you, how does a refrigerator work? What would be the simplest explanation you give them? If you say that it removes heat from colder to hotter, that's not an explanation, that's just describing what it does, the outcome. But how exactly does it do it? How do you explain the working of a refrigerator?
Take the thermal energy from the space and then. Yes.
So what the refrigerant, essentially what they do is they basically compress it, in the sense they increase its kinetic energy, make it flow in a circuit where when it encounters heat, it's going to undergo phase change. It will go from liquid to vapor. That is, it picks up heat from your inside of the refrigerator, evaporates, becomes a gas, and then goes through the pump where it is condensed back and then recirculated again. Now, part of it is thermodynamics, part of it is heat transfer, but the fluid mechanics bit comes in pump selection. How do you select a pump to decide which pump to use to get a refrigerant to circulate around the circuit? What factors do you think go into selecting a pump? Even without fluid mechanics, if as an engineer people ask you, hey, how should I pick out a pump? What are some of the factors that go into your thinking?
The amount of fluid that's coming. The amount of fluid.
The flow rate, right? So in pump selection, one of the main consideration is how much flow that you need to circulate. Q. Good. What else?
Density of the fluid.
Density of the fluid. Okay. And it also is determined by the diameter of the piping that you use in a sense. And then the viscosity of the fluid. Why viscosity?
For viscous fluids take stronger from the pump.
Viscous fluids dissipate more energy, which means your pump has to work harder, right? So all these together determine the pressure drop that is created. That is, what is pressure drop? Why would pressure drop? So let's say you have your water tower to begin with. The water is static there. There is a huge pipe that runs from the tower down to the village that is at the ground. Once the water flows down, it comes in with a lot of energy because it's obviously converting the gravitational potential energy to kinetic energy. What causes the pressure to drop? What are all the factors that can lead a fluid to lose its kinetic energy? Obviously, viscosity is one. If you have the fluid coming in with a lot of kinetic energy, viscosity or friction will steal the kinetic energy and slowly convert that into thermal energy. What else can cause the fluid to undergo pressure loss or loss of kinetic energy?
Change in pipe diameter.
Change in pipe diameter. So let's talk about that. So if you have a pipe that's going this way, and then suddenly the diameter drops to a lower cross section, this will cause some loss. We are going to see how or how to quantify it. But why do you think this causes loss? Why would there be a loss of kinetic energy when the fluid tries to reduce its cross section? Just intuitive answer. I'm not looking for a deep explanation. Why would there be a pressure loss or loss of kinetic energy when the fluid abruptly undergoes a decrease in cross section? Okay, keep that question in mind, and as we go through this topic, see if you can figure out the answer. Okay, so now I'm going to go back to a little more structure and stop with the brainstorming. Okay, so let's start with the basics here. Pressure difference causes flow. That's the basic fact. So if you have a pipe, okay, and let's say this pipe is connected to a reservoir, okay. So this is the reservoir, like your tank, and this reservoir is filled with fluid, okay, and this fluid, if it has, let's say if it is at a certain height that is much higher than the level of the tube, this weight of the fluid is going to drive a flow. So in this case, the static pressure of the fluid in the reservoir drives the flow. So let's look at this flow in some detail. What happens when the flow enters the tube? So the flow enters the tube, and initially this flow is driven by the pressure difference or the pressure head that exists in the reservoir, and this flow essentially comes into the tube, and this flow is going to be velocity equal to the flow rate divided by area. It's uniform to begin with. Why would it be uniform? Because over here you have the reservoir. The fluid molecules are only in contact with themselves. They have been previously at rest, and now they are trying to flow through the tube. Okay. Now answer this for me. What happens at the walls? What happens at the wall where fluid comes in contact with a solid surface, that is the pipe or the tube, that is at rest? What do you think happens there? Fluid coming in contact with a solid surface.
It'll hit the wall and bounce away.
No, we are talking about the flow flowing parallel to the wall. It's flowing past the wall.
Yeah.
What do you think will happen?
Sure.
Friction. Okay. Can you please say that in a full sentence?
The fluid as it flows against the wall, there's friction happening to slow that part of the fluid down.
So friction at the wall will flow the fluid down at least the layer that's in contact, at least the layer that is in contact with the wall. Okay, so I'm sorry, I wrote it a little staggered here. So this is where our story starts. Pressure difference causes the flow. And in this case, the static pressure of the fluid drives the flow. And then the question I posed is, what happens at the wall? So to that, I have added 2 bullet points. Fluid comes in contact with the wall, and that causes friction. The friction slows down the fluid or the layer of the fluid that is in contact with the wall. You're with me so far? So if you think about the flow here, okay, so when it enters the pipe, the flow is uniform. The velocity profile is uniform when the flow enters the pipe. A little bit down the line, what happens is wall friction and fluid viscosity lead to slowdown of the fluid layers in contact with the wall. Over a small distance, this happens where friction acts on the fluid, and because the fluid itself is viscous, what happens is, if you think of this picture, I'm drawing this kind of big here, you have a portion, the fluid that is in contact with the wall is at rest. The fluid that is immediately in contact with the wall has to come to rest, which means the fluid that is moving right next to that has to slow down a little bit. The fluid that is right next to that has to slow down a little bit more. And then they slowly merge with what is then the rest of the fluid where the flow is uniform. So you have 2 zones here, okay? We'll call this zone as the inviscid zone where the effect of the wall has not yet been felt, and this zone as the viscous zone where the effect of the wall has been felt. And what is the effect of the wall? Slowing down of the fluid. Okay, so in viscous zone, wall has been felt. This is still untouched by the wall or the presence of the wall. Okay, this happens a little bit as you go downstream, as you go along. Okay, as this fluid goes along, the pipe, what do you think will happen? As you go more downstream, what happens? This effect will continue, right? If this effect continues, what will happen to this velocity profile?
Comes in a curve.
Instead of saying the outcome, just tell me what is happening. Describe in words for me. It moves forward. More and more regions or more and more portion of the flow will feel the effect of the wall. That's what I mean. That's what you also mean. Becomes parabolic because that's a mathematical fact or outcome. But what happens is, let's say we are all 10 of us are lining up here, and I am the one that is closest to the wall, and we all hold hands. I hold my hand to the wall like a like a something on the wall here, and I just stop. I am holding my hand with the next guy, and he's still trying to walk, but my hand will pull him back. And his hand will pull the next guy back, and over time, what will happen is we will form a parabolic profile in the sense that some of us are still trying to walk, but some of us are slowed down. That's what exactly happens. So as you go downstream, what happens? The flow profile becomes more viscous, and the region that is untouched by the fluid viscosity of the wall becomes narrow. Okay. So if I draw this a little bit down, what happens is this becomes even more viscous. It's still not yet parabolic, it's still only getting there, whereas you still have an inviscid zone, and then you have a viscous zone. Continue this thought experiment. If the flow continues on along this direction, what will eventually happen? The effect of the wall or the viscosity will be would have fully percolated and get you a flow profile that looks fully viscous. There is no portion that is still inviscid, and this portion is fully viscous. Are you with me so far? What happens when a flow enters a pipe? That's what we are talking.
So the one where it's fully inviscid is 0.1. And then the one where it gets less inviscid is 0.2, and then less and less,
What is 0.1 here?
like where it starts.
No, I'm just saying at the entrance it's fully inviscid.
Okay. And
At
then
the entrance, it's fully inviscid. Then what happens is, as you move from the entrance further inwards, it becomes more viscous and the inviscid zone starts shrinking. And at some point, you reach a situation where the entire flow profile has been influenced by the wall and the fluid viscosity, and you get what is called as a fully viscous profile. With me so far in the story? Fine. Good. So this distance from the entrance to where the profile becomes fully viscous, this is called entrance length. It takes a finite length of piping for any flow to develop and become fully viscous, and we just call it the entrance length.
once it reaches full viscosity, does it stay like that for the rest of the pipe?
Exactly. Once you reach this fully viscous profile, unless something else is going on in the system, if it's a steady flow and nothing's changing, this flow profile will remain so further downstream. So what is critical is, if you are having a pipe flow over a certain length of pipe, you need to have a sense of how much is the entrance length as a function of the total length of the pipe. Sometimes the entrance length might be a tiny fraction, most often it is. Sometimes it could be a significant fraction. Okay, so we need a way to estimate entrance length. Okay, so how to estimate entrance length? That's a question that we have to be able to answer. And if you watch the video, I go in a little more detail in explaining this, but pretty much the same idea, maybe some more details. Okay. With me so far? Good. Okay. So if we think about, we'll come to entrance length in a minute. Okay. I want to talk about this fully viscous flow profile and kind of make an analysis, like a scaling analysis, wherein if I have a pipe flow that is fully viscous, or we call it fully developed, where you have a flow velocity Q, you have the pipe diameter D, the fluid has a viscosity rho and has a density, viscosity mu and a density, viscosity mu and density rho, okay, and over a length, that is over a certain length of the piping, the pressure drop is delta P. Why would there be pressure drop?
Because you'd decelerating.
Because there is friction at the walls. The friction is constantly eating away the kinetic energy content of your fluid. That's what causes the pressure drop. If your fluid entered with, let's say, 30 psi G of pressure, because of flowing through the tube, it could drop to something like, let's say, 29 psi G. 1 psi was essentially lost because of the friction that happened between station 1 and station 2. Okay, so before doing the derivation, let's do a scaling analysis. If I told you the pressure drop across a length of pipe depends on the length itself, depends on the flow rate, depends on the diameter, and depends on the viscosity as well as the density of the fluid. From these, can you express this in a non-dimensional relationship? This is a very good problem for our exam, where it could be problem 1 or 2. How do you express this using scaling analysis? What is a good reference length here? D, right? D is a good reference length. Okay. So Q here, I mean, it depends on Q, but typically what they do is they think about Q as V times A or V times pi d squared over 4. So instead of Q, it's typical to use velocity or the average velocity. Okay, so I'm going to say let's think of the problem in terms of V. If V is one of the quantities that influence the pressure drop, and we have already selected diameter for reference length, what is a good choice for reference time? You have a velocity, you have a length. How do you combine them to get a reference time? Distance over velocity. That's what you mean, right? That is, if you want T ref, you can take it to be D over B. Can you not? Yeah. Okay, you have selected a length, you have selected a time for reference. Then we need to select a reference mass. So M reference can be rho d cube. So I used up diameter, velocity, and density. Now I have length, I have viscosity, I have delta P. I can easily normalize length as length divided by time, diameter. So delta P is a function of length divided by diameter, and then I have to take viscosity and normalize it somehow using L ref being B, T ref being D over V, and M ref being rho dq. Is the problem making sense? Elijah, are you okay? Christina, good? Okay. So what do you do about viscosity? viscosity, what are the dimensions of viscosity? What is the definition for viscosity? We had the same discussion maybe. Viscosity is defined as shear stress divided by the velocity gradient that's causing it. So with dimensions of viscosity would be shear stress or Pascal, velocity gradient is speed divided by length or per second. So the unit for viscosity would be Pascal second, and dimensions of viscosity would be, what is Pascal? Newton per meter squared times second. What is Newton? Kg meter per second squared divided by meter squared times second. So this is mass per length per time. So to normalize viscosity, you need to take the reference mass multiplied by the reference length inverse multiplied by the reference time inverse, which gets us viscosity divided by rho dq multiplied by d to the minus 1 multiplied by d over v to the minus 1. So which gives us mu times rho d v. So mu divided by rho d v. So delta P divided by something is now a function of L over D and mu over rho D V or rho VD. I will call it rho VD because that's the more commonly used. And how do you normalize delta P? What's the dimension for delta P? Dimension for delta P would be, just forget the time here. So you would have mass per length per time squared. So you would have delta P divided by rho dq, per length is d to the inverse and per time is d over v to the minus 2. That gets me delta V divided by rho d to the minus 1, d to the minus 2, so that goes away, times v squared. So I get delta P over rho v squared. So delta P over rho v squared is a function of L over D, and instead of this I'm going to write rho Vd over mu. So this scaling tells that delta P over rho v squared depends on length of the pipe as well as this quantity rho Vd over mu. Okay, with me so far? If your pipe length is more, it will scale with that. And then this quantity, rho Vd over mu, is called as Reynolds number and is encountered whenever fluid viscosity is non-zero. Whenever fluid viscosity is non-zero, what does that mean? How to think about Reynolds number? Let's talk about that.
You can just flip them, the ratios, whatever, if you want to.
I mean, it's like saying if I have a function of x and let's say it appears as c over x squared, something like that. You can also call this a function of 1 over x and say this is c times 1 over x squared. It's just a notation to say it depends on this ratio. Whether it depends on the ratio or the inverse of it is just mathematical detail. But it depends on this ratio. That's the critical. Okay. Let's try to give an interpretation, physical interpretation of Reynolds number, which is rho Vd over mu. Okay. Now answer this for me. What happens at the walls? What did you tell me? What did you tell me happens at the walls? There is the wall and then the fluid that is in contact with the wall. What happens? The wall exerts a viscous force or a shear force on the fluid, correct? So if I think about the fluid velocity profile in this vicinity, it's viscous here, and then it is inviscid here. Inviscid meaning free from viscosity. Inviscid. Okay. So if I think of a control volume that is about this big here, that includes this viscous portion, can you tell me what are the forces that are acting on this control volume, which includes the wall, the surface of the wall, and the viscous portion of the fluid? What is the main force acting on this control volume? So the flow comes in with certain momentum. So when the flow leaves, there is a momentum deficit. Some momentum has been taken away. Who is taking away that momentum?
Friction.
The frictional force at the wall. How should I draw the frictional force?
Right from the direction.
So it should be an arrow pointing in the backward direction, and it has to be a frictional force, basically like a shear stress at the wall, multiplied by the area of the wall. Do you agree with me? I mean, you have to think of this in a cylindrical geometry. So you have a pipe, you take a certain length along the axis. In that ring shape, the fluid is coming in with some momentum. The wall is exerting a force on the fluid and stealing momentum. That's all that is happening. If you come in with some momentum, you leave with a little bit less, and that less is essentially siphoned out by the wall. Okay. So what we want to think about is how much force or what is the order of magnitude of this force. You want to think about the shear stress, which you can write as viscosity times velocity gradient. That is the definition for viscosity. And we have to multiply this wall shear by the area in contact. Okay. So this will scale as viscosity over this distance. How much should I think du over dy would be? What is a reasonable way of thinking about it? Don't do sophisticated math. Just tell me over a certain length, and we'll call this length as delta. How should I estimate du over dy? The fluid's velocity at the inviscid portion, we'll call it u. Okay, we'll call it b. B is essentially q divided by the total area at the beginning. B. and this distance is delta. So what is the approximate magnitude of the velocity gradient or the drop in velocity in this gap? You are at V, from V
Change
at the wall you go to 0. So how much is the approximate drop?
V over delta.
V goes to 0 over a distance which is delta or V over delta. Right? So the wall shear is mu V over delta. Okay, and all I'm trying to do is give you some meaning for this Reynolds number. I can just say it's the ratio of this and that and just move on, but I'm trying to see if we can make a connection with it. Okay, and what is the area in contact? What is the curved surface that is in contact? How do you calculate curved surface of a cylinder? Pi r squared times length. Right? Area of a curved surface of a cylinder is pi r squared times length, right? So if this portion has a length L, this area would be pi r squared over L, or I'll write this as pi by 4 d squared times L, where L is this length.
So I got a question about that.
Yeah.
I don't know if it works the same as like a meniscus, but a meniscus is elliptical, which is a different equation for area.
And a meniscus is formed for a completely different reason. It's another property of the fluid called surface tension, where the force between the molecules are holding them together against gravity. Over here, we are talking about viscosity, which is basically the force between the fluid layer and the wall, or between the fluid layers themselves. Okay, surface tension is basically, surface tension comes into effect only when you have a fluid and material A and material B, meaning if the fluid likes itself more than the solid surface on which it's resting, it will not spread like MECH. If it likes the material surface more than itself, like water, it will spread. We didn't talk a lot about surface tension in this course. That is a completely different physics than this. So we'll just stick to viscous or frictional forces. Okay. So this is the shear force or an approximation for the shear force acting on the fluid. Okay. Now, how much momentum does the fluid bring with itself? That is, if you have a flow with a velocity v, how much kinetic energy are you bringing with yourself? What is kinetic energy? Half m v squared. Yes.
Is the area supposed to be the surface area of the edge of the interior? Or
Yeah, the curved surface. That's what this is.
It shouldn't be 2 pi r then? Maybe the circumference times length.
Yes, sorry. So that is what I wrote as volume. So 2 pi r L, or this is pi d L. So I can write pi d L. Correct. So then I'm asking, what is the kinetic energy of the fluid? How much mass of fluid is contained in this volume?
V times delta over 2.
Come again?
V times delta over 2.
V times delta over 2. No, what I'm asking is mass will be density times volume. Volume being No, wait, hold on. I don't want to get into kinetic energy right now. The next step I should be doing is to think of how much energy is associated with one, the motion, or in other words, the velocity of the fluid, and friction, which is related to viscosity. How do you estimate energy associated with motion? That would be kinetic energy, energy associated with motion, also known as kinetic energy, scales as half m v squared, which is half rho d cube times v squared. Because I'm just making an estimate, if I take a typical volume d cube, I'm going to get a density rho, and that is my approximation for the amount of mass. Okay, I'll drop this factor half because we are doing only scaling, we don't have to be very precise. So this is rho d cube v squared. Okay, and what is the energy associated with friction at the wall? How do you connect, or how do you estimate the energy dissipated by friction at the wall? So if you take the shear stress, that is mu times du dy, and we can approximate that as mu times v over delta. That's what we did here. Right? How do you go from stress or pressure to energy? Stress multiplied by what gives you energy? Think in terms of dimensions. What is stress? Newton per meter squared. Multiplied by something gets you energy, which is Newton meter. When we did Bernoulli equation, we saw pressure is nothing but energy per unit volume. It's basically energy density. So if you had a volume here, you would get energy. So this quantity multiplied by dq will, I'll write it separately. Mu v over delta multiplied by dq is the energy associated with friction. Okay, so two quantities to remember: rho d cube v squared and this quantity. So I told you that when it happens closer to the wall, we consider that to be delta. But when the flow becomes fully viscous, when the flow becomes fully viscous, what happens to delta? Delta becomes what? It's no longer confined to a small region near the wall. The entire cross section becomes viscous. So what happens to what's the magnitude for delta? It's the radius of the pipe. That is, delta becomes the radius of the pipe or half of d. So we can take mu v delta times dq is approximately same as mu v over d times dq, or this is mu times v d squared. So here is the two energies. What is the energy, or what is the kinetic energy? That scales as rho dq v squared. What is the frictional energy, or the energy dissipated by friction? That scales as mu d squared v. And let's get the ratio of these. Ratio of this will be rho dq v squared divided by mu d squared v, which is rho v d divided by mu, which is what our Reynolds number is. So now that I have established Reynolds number is the ratio of kinetic to frictional energies, can you provide an interpretation for that ratio? What does high value of that ratio mean? What does low value of that ratio mean? So Reynolds number is rho Vd over mu, can also be written as rho v squared dq over mu v d squared, the numerator being an estimate for the kinetic energy of the flow and the denominator being the energy dissipated due to friction or fluid friction, which we call viscosity. Okay, so what does that tell you about this ratio? If this ratio is a very high number or a very low number, what does it tell you literally?
It's a high number, more energy is being dissipated because of the kinetic energy of flow. It's a low number, then more is being dissipated due to friction.
The way to say that would be, you're kind of right. If Reynolds number is high, let's say it's like 100,000. This energy content of the flow, who provides that energy? Where does it come from? From where? Through movement, which is usually initiated by a pump or a pressure head. So this kinetic energy is a direct function of how much work you had done to provide it to the fluid. The fluid has to get it from somewhere, right? That somewhere is usually a pump. So this kinetic energy is coming from the energy input into the flow, and this energy dissipated due to friction. What is the origin of that dissipation? Wall friction.
Yeah.
The energy dissipation is coming from wall friction. So if you had a flow in which you had a high Reynolds number, let's say Reynolds number happens to be 100. Literally, what does it mean? Just based on this, literally, what does it mean to have a Reynolds number of 100?
You're 100 times, there's 100 times more kinetic energy than there is energy dissipated due to friction.
There is 100 times more energy available in the flow based on the nominal flow values than what the friction can dissipate. Okay, if Reynolds number goes up, let's say you go from 100 to 1,000 to 100,000 to a million, or if Reynolds number goes down, say you go to 10 or 1 or 0.1, what does it mean to go higher in the energy in the Reynolds number scale, and what does it mean to go lower in the Reynolds number scale? Let's talk about higher first. Let's say you have a Reynolds number of 100,000. What does it mean? It means, like you said previously, there is 100,000 times more energy available in the motion of the fluid than what is being dissipated by friction. With me? That's how you would literally interpret it. Reynolds number 100,000 means the fluid has 100,000 times more energy than what friction can dissipate. Okay? What is the implication of that? So let me pose the question, we'll come back and answer it. What happens when Reynolds number is much greater than 1? So we keep 1, actually 1 is the cutoff point, I should have drawn it like this. Okay, anyway, what happens when Reynolds number is very high? On the other hand, let's say you go from 100 to only 10 or only 1 or only 0.1, what is the implication of Reynolds number being a very small number?
It's 0.1, it means that there's 10 times more energy dissipated due to friction than there is kinetic energy of the flow.
So if you say that it's 0.1, it means the friction is dissipating 10 times more energy than what is present in the motion. That means that flow is literally circling the drain, because soon the friction will take out all the energy and convert it or dissipate it into heat. If you don't keep pumping, that fluid will soon come to rest. Do you see that? If you have a low Reynolds number, it means friction is doing more dissipation than the available energy content. Which means if you don't prop it up, if you don't pump it, the fluid will immediately go to rest. So low Reynolds number means what? It's viscous dominated flow. So if that is the case, what does high Reynolds number mean? What does high Reynolds number represent? What dominates high Reynolds number flows?
The other, forgot the other term's name. And this starts with the L.
So the other regime, that is the high Reynolds number flow, is punctuated by high kinetic energy. If you are, let's say, running in the field with a lot of kinetic energy, and when I try to stop you, what do you call that you had before I tried to stop you? You know this term, starts with I. Say inertia. So low Reynolds number is called viscous dominated regime, whereas high Reynolds number is called inertia dominated regime. Okay, so we have established Reynolds number for the very first time in this course. Reynolds number Reynolds number not is, can be interpreted as the ratio of inertial energy to frictional or viscous dissipative energy. It's not viscous dissipative energy, it's energy associated with viscous or frictional dissipation. Okay. I can't seem to say anything elegant. Reynolds number can be interpreted as the ratio of inertial energy to the energy associated with frictional or viscous dissipation. So if I wake you in your sleep, this is what you're going to tell me. Reynolds number can be interpreted as the ratio of inertial energy to the energy associated with frictional or viscous dissipation. Viscous dissipation is a process, meaning how does that process happen? How does viscous dissipation happen literally, microscopically? It happens as the wall exerting a tugging force on the fluid layers and that force propagating through the fluid. It's a process that basically works because at the wall, the fluid that is in contact with the wall is at rest, which means it pulls back a layer of fluid, that pulls back another layer of fluid, that pulls back another layer of fluid, and you get what we call as a viscous velocity profile. That is a process, and that process can happen only if there is a wall, right? Only if there is a wall, you can have wall friction, right? Whereas this kinetic energy of the flow, if you take an arbitrary mass of the fluid that is moving at some speed, it will have kinetic energy. That's just mass times velocity squared, right? So Reynolds number serves as like a yardstick to kind of quickly tell us whether that flow is dissipated by the fluid's own kinetic energy or the walls or the fluid's viscosity. If Reynolds number is high, what's your first instinct? It's an inertia dominated flow. It has a lot of kinetic energy to work with. If it's low, or if Reynolds number is low, what does it mean? It's a viscous dominated flow. It has more dissipation, which means without intervention, the fluid can't go far. Here's one example. You're doing your soap experiment, right? If you take your soap, and for reference, you also take water, okay? Take an inclined plane, just gently place the soap or at the top of the incline and gently place or gently drop water at the top of the incline. Which do you think will flow farther?
Water.
Why? You gave both of them the same energy or same pressure head, but one of them flows lesser because
The more friction.
the friction basically heats up the kinetic energy faster with soap than with water. So next step in our progression, we have only 3 minutes here. I want you to try this exercise now. We'll continue on Thursday. Okay, let's think of a fluid like air, whose density is 1.2 kilograms per meter cube, and viscosity is about 10 power minus 5 Pascal seconds. And let's say we have objects and speeds and corresponding Reynolds number for them. Can you tell me some typical speeds? If you are a baseball fan, what is the typical speed of a baseball? What is the typical size of a baseball? 4 inches, and speed is maybe
It might be like 95.
let's say 100 miles per hour.
Yeah.
So what I want you to do is calculate the Reynolds number for if you are pitching the baseball, you can think the air is stagnant and the ball is flying through, which means in the perspective of the ball, you can consider the ball is at rest and the fluid is flowing past the ball. What will be the Reynolds number associated with a baseball that's flying at 100 miles per hour? You can calculate this. I want you to calculate this. Okay. Let's think of another situation. Any golfers? What's the size of a golf ball typically? Maybe 1.5 inches.
Yeah.
And what's the size of what's the speed with which the ball is typically hit, or at least in a long shot?
170.
What's the Reynolds number? Okay. how many tennis players here? What's the typical speed in a tennis shot? In a backhand or a volley or something?
Only about 40 miles an hour.
40 miles per hour, and the ball is maybe 3 inches, 4 inches.
No, it's about the same size as pickleball. Yeah.
What's the Reynolds number? I mean, you don't have to be a genius to say this. Between these two, which has the lower Reynolds number?
Tennis ball.
Why? Because Reynolds number scales with velocity to the linear power. You can in fact make a more precise prediction. The Reynolds number for a baseball will be twice as much for the Reynolds number for the, not twice, 2.5 times the Reynolds number for the tennis ball. Okay, last thing. Forget sports. How fast does a bullet fly? How many? 30 what? What unit 30?
A bullet flies at around, I only know this in meters per second, it's like 500 meters a second.
We'll approximate it as 1 kilometer per second. Okay, or even, okay, let's say 500 meters per second, half a kilometer per second. And what's the size of a bullet? Maybe, like there are so many caliber bullets.
Ranges, but caliber that would be easy is 9 millimeters.
9 millimeter. Okay, so 9 millimeter and 500 meter per second. What's the Reynolds number? And if you had another caliber, does anyone who knows about bullets tell me what is another typical caliber size?
5.56 is
Come again?
5.56. I don't know what it is in millimeters.
Maybe 12 mm. Let's say 12 mm. 12 mm and similar speed.
It go like 8.
What will be the Reynolds number?
It go a little faster, maybe like 700, 800
Let's say 750.
approximately.
Okay, so what I want to know is between the two bullets, the 12 mm caliber versus the 9 mm caliber, what will be the ratio? They vary in size, but they also vary in speed. So Reynolds number scales with both diameter and velocity. So if velocity is 12 and 12 by 9 times, this is 750 divided by 500. So that gets us 4, 3, 250, 2, 2. So the Reynolds number ratio should be 2. Okay. So next lecture where we are going to continue is to continue estimating Reynolds number for some typical flows that are through pipes. What is the common thing between all of these balls and bullets? They are all external to the object. They are called external flows. We are interested in pipe flow because we are hoping you all would find jobs in biomedical or HVAC or nuclear or power plant industries. So we want to teach internal flows. So next lecture we'll continue with this Reynolds number discussion. Okay. Last thing, please listen, please watch the videos. I want you to spend 30 to 40 minutes daily until Monday and watch through all of them. Okay. Thank you.